You're welcome. Again, we continue with set logic and algebra, and we're continuing with chapter 1 and precisely relations and functions. Again, my name is Dr. Lois Adewoye Ademola, and on the screen you see the topics we'll be covering in this video, so you can pause the video and scan through or look through them. Okay, we begin with definitions. The first definition is what we call a binary relation. So a binary relation from a set, so we have two sets, set S and set T, assigns to each other pair, so we have A, B, with this direct product, exactly one of the following statements. So it's either this, X is related to Y, X is not related to Y. Okay, a relation from a set S to itself is called a relation on S. So that's another definition you need to know, what a relation on S is. Now we say a relation is a relation with this notation, tilde, more like a snake sign. Okay, so this relation, a relation on a set. So we have a relation defined on a set, and you know what a binary relation is already from up this definition up here. Is when you have a relation on a set, it is called reflexive. Okay, if A is related to A for every A you pick in the set. Okay, we'll be considering some examples, so don't worry about that, just know the definitions. So the next definition is that we say the relation is symmetric, and that happens when for any A comma B you pick in S, okay, you have that A related to B means that B will be related to A. A good example is siblings in a family. So, and the relationship to there being siblings. So you can say if Tabitha, Hawa, and Hassan are from the same family. So Tabitha, let's take T to be Tabitha, small letter T means an element, and Hassan. So being siblings means that Tabitha will be related to Hassan, right? And it is true that Hassan is related to Tabitha. Why? Because they are siblings. Okay, so that settles that for relationship. Okay, so the next definition you to know for a relation is what we call transitive. It is transitive if A is related to B and you have B to related to C, then A is related to C. Okay, so in the case of that relationship of siblings, if Tabitha, so let me take Tabitha, Hassan, and what was the last person? Let's just and Hawa. So let's say Tabitha, Hassan, and Hawa. Let's put a H for the small Hawa. So if Tabitha is a sibling of Hassan and Hassan is a sibling of Hawa, clearly Tabitha is also a sibling related to related to Hawa. So that is what we mean by transitive. So this relationship is transitive. We say it is transitive. And so you need to know this definition by heart because we'll be using them practically in most of the video. And the last one you need to know is what we call an equivalence relation. So an equivalent relation, this two that is a relation. This is called an equivalence relation if it is reflexive, symmetric, and transitive, meaning that if these three properties here hold, we say the relation is what? Transitive. So it's an equivalence relation, not transitive. So once the three condition holds, we have an equivalence relation. Okay, so you can pause the video and then go through the definitions again. Expected to know them by heart. Okay, let's continue to the next slide. The next definition you need to know is what we call an equivalence class. What's an equivalence class? So we have tilde is an equivalence relation on a set. So first you have an equivalence relation, meaning that it satisfies the three conditions here. That is, it is reflective, symmetric, and transitive. So if we have an equivalence relation, then the equivalence class of all elements in X in this set, and we denoted this S with a subscript X, so X in S. So the collection of all of these X's, okay, that satisfies the relationship that X is related to Y for every Y in S is called an equivalence class. So if I happen to have X in S, so that X is related to Y for all Y in S, then we say we have an equivalence class. It collects all of the X's that satisfy that relationship. Okay, so sorry, Y in X, it collects all the Y's that relate with X. So that's the right definition, not the X but the Y's that are related to X. So that's what we have as definition for an equivalence class. The next definition you need to know is this subscript, this quotient here, S slash with a tilde. Okay, this collection of equivalence class of S denoted this is called the quotient of S by tilde. Okay, so the quotient, the collection of all these equivalence classes is denoted this. You can see that the equivalence class, so it's simply just saying you collect all the equivalence classes such that X lies in S. Okay, so you know the two definitions now. In fact, you know all the definitions, so you can rewind the video and know the definitions properly. The next thing you need to know is what we call a partition. So what's a partition? Now, a set S is a subdivision, so it's a partition of a set S. So a partition basically it breaks the, so if you happen to have a set S and it has elements, it will just break them into compartments, like, okay, with satisfying the condition of an equivalence. So let's read what it says anyway. Okay, so the definition says a partition of a set S is a subdivision of S into pairwise disjoint non-empty subsets whose union is S. Pairwise disjoint non-empty subsets. So they are disjoint, they are non-empty, okay, and pairwise disjoint, right? So you have two of them. You can't have elements within them together. Whose union? So when you take the union of all the elements, you get back the set S. Okay, that is a partition. So definitions like what is a partition, what is an equivalence class, what is an equivalence quotient, okay, the quotient, what is an equivalence relation, what is, when is a function said to be reflexive, symmetric, and transitive. Those are definitions you need to know. What is a relation? So you need to know them by heart. Okay, another definition you need to know is what we call a poset. Okay, we call it simply a poset. Okay, but before we define a poset, you need to know this relation. We say a relation, notation different now, more like less than symbol, okay, less than or equal to symbol. Okay, so I'm using a different notation here, but you will know why. So a relation with this notation on a set S is said to be a partial order, not partial order. When do we have a partial order, or simply an order? So we can say it's an order or a partial order on the grounds that it satisfies this three condition: reflexive, similar to what we had. Remember when we were doing that of reflexive for the equivalence, we had something like this, right? But now it's a different notation, as you can see on the screen. Okay, so the partial order happens when we have the reflexive relation, a transitive, similar to that of equivalence relation, right? But now we're defining a partial order, and antisymmetric, not antisymmetric. Look at the definition for antisymmetric. In the case of the symmetric, we had A related to B, B related to C, meant that A was related to C. But in this case, we have the condition that if we have, okay, sorry, it was symmetric. Symmetric, we had A related to B and B related to A, right? But in this case, we have an extra condition which makes it antisymmetric, meaning that if A is related to B and B, are you seeing, is not related to A, so there's a not, okay, then A must be equal to B. So that's the antisymmetric. So that's just a difference between the equivalence and the the partial order. Okay, a partial order simply means that it satisfies reflexive, transitive, and antisymmetric. Noting the definition for antisymmetric, because now you know that of transitive, you know reflexive, and you know symmetric. Now when you have symmetric, transitive, and reflexive, you are talking about the equivalence relation. But for the partial order, you need these three conditions, as you can see on the screen. Okay, so what we simply say is that A precedes B. That's just what it means. Okay, if A precedes B, or A is contained in B. Now, the next definition you need to know, which is what I've been calling since, is what we call a poset, a partially ordered set. Now, you know what a partial order is. So what happens? A set with a partial order, if it has a partial order, is called a partially ordered set. Simply put, a poset. Okay, so that's all you need to know. And it is denoted as S because of the partial order on it. You put it in a bracket of this form. That's the denotation. Now, two elements X and Y in a poset are said to be comparable. So you could be asked, when are two elements in a poset said to be comparable? They are comparable if either X precedes Y or Y precedes X. Okay, that's when we have that. And the poset is called a totally ordered set or a chain. Okay, so if it's comparable, it's either that X precedes Y or Y precedes X. And when that happens, we say we have a what? A poset that is totally ordered. Okay, so we have total order. You need to know that it is what? A total. Where is it there? Yes, totally ordered. It is totally ordered when we have that. Okay, now a greatest element of X, that is a subset of the poset, is an element G in X such that G precedes G. X precedes G for all X in capital X. The next definition is a maximal element. For a maximal element in the poset, a subset X of a poset is an element M in X such that for all X in X, M precedes X, then M equal to X. We will need to know these definitions, but we will use them later in examples. So for now, know these definitions by heart, and then we'll see them being applied shortly. Okay, the next definition you need to know is what we call the least element. We defined the greatest element earlier on, and we also defined the maximal element. So the least element is almost similar. This element of a poset is an element E in S, such that E precedes X for all X in S. And for the minimal element of a poset, we say it is an element V in S, such that for all X, whenever X precedes V, then X is equal to V. Again, you need to know these definitions by heart. Now, I refer to the lecture notes. You can check with the cyber cafes around the institution. You should be able to get the lecture notes on Maths 203 or see students who had taken the course earlier. Okay, you'll get the hard copy of the lecture notes. So please do that for further information on definition of function, injective functions, surjective functions. You could also Google, you get them on the internet too. So let's continue. The next thing you need to know is a very important lemma or theorem, as the case might be. It is called the fundamental theorem of equivalence relation. I would expect that you will be able to state the fundamental theorem of equivalence relation and also prove it. It states that let tilde be an equivalence relation on a set S. Then the quotient S modulo tilde forms a partition of S. Now you know what this definition is, this quotient, and you know what a partition is. If you don't recall, you can rewind and go backwards to get the definitions again. So now we want to show that you have tilde. It is an equivalence relation. When you have an equivalence relation, meaning that it satisfies reflexive, symmetric, and transitive. Now you're having this and you're saying that once you have this, then this quotient forms partitions of S. What's a partition? It means that it breaks them into subsets, subdivisions, right? Okay, so if it breaks them into subdivision, that's our target. We can prove by contradiction by assuming that it doesn't break them into subdivision, because the subdivision means they are what? Pairwise disjointed. Okay, so we want to say that that's not the case. They're not pairwise disjoint, and see if we'll get a contradiction. Okay, so this is how the proof goes. It says, suppose that tilde is an equivalence relation on S. So it means that S has the condition that it is reflexive, transitive, and what? And sorry, I jumped it. Reflexive, symmetric, and transitive. Okay, so there's three conditions. So if it's satisfied that, we shall prove that any two equivalence classes, remember, because it's an equivalence relation and we have this quotient, it means that something has to do with equivalence classes, right? Because this is a collection of all equivalence classes. So any equivalence classes, so we pick two of them in terms of X and in terms of Y, are either disjoint or they coincide. So we want them to either be disjoint or they coincide. So we have two equivalence classes, Sx and Sy, that are disjoint, meaning that if you take the intersection, it's not empty, there are elements in them. Okay, we may choose A in this intersection because it's not empty, right? So we can pick them. Okay, so recall that this definition for the equivalence classes, remember what I said, we have X, if you recall, in S, such that X is related to Y for all Y in S. That's just what the set is saying. You can also rewind to get the definition. So now we know what this definition means. It means that if I happen to have this definition based on the element M, and we already said that, so M, in our case now we have Sx and Sy. We already said that these two are disjoint, so we have picked an element A in it. So we know that A is in this, which means that by the definition of Sm, in our case we have Sx. It means that wherever there is X, M, put X there. It means that X is related to all elements N, right? But there's A in it, so for all in A, right? And same also will hold for Sy. It means that X related to, sorry, not X, but A related to. I keep interchanging them. I shouldn't be interchanging them. Don't make the same mistake I've made, okay? Based on the definition, it's saying that from here, you can see that it's supposed to be N is related to all elements in S. That's M. So this is it's supposed to be interchanged. Okay, so it means that X related to X because A is in Sx and it's also in Sy, right? So X will be related to X. Sorry, X will be related to A and Y will be related to A. Meaning that I can have conditions further from this condition. How? I know that my relation is an equivalence relation. It is reflexive, transitive, and it's also symmetric. If that is the case, with this new development based on this interpretation here, if X is related to A and Y is related to A, by symmetry, I will get that Y is related to A. Note from here. Symmetry means that if I have A related to B, then B is related to A, right? So if Y is related to A, then A will be related to Y, as you can see on the screen, based on symmetry. And also by transitivity, I have another one that can hold. So this satisfies this. You have A moving all the way and A relating to Y here. But I know that this A going to Y, I know that X is going to A. And if X goes to A and A goes to Y, what do you conclude? You can see, because I had said before for transitivity that if A goes to B related to B and B is related to C, it means that A is related to C, right? So based on that, you can see that X related to A, which is we got from here, and A related to Y, which we got from the transitivity from 1, that from 1 it implies that X is related to Y by transitivity. Oh, if X is related to Y, it means that X and Y are related somehow. And see it here, it means that X lies in Sx by 2. So automatically, we're proving that Sy is actually contained, sorry, I'm moving it backwards. Okay, so meaning that Xy is contained in Sx. In the same way, if you follow the same argument as I've shown on the screen, you get that Sx is contained in Sy. Once you have the two containment, it means that Sx is actually the same as Sy. So That's what I've typed here. It says in a similar way, it is easy to show that Sx is contained in Sy. Therefore, Sx is equal to Sy. So we conclude that this quotient partitions S because it's either they are disjointed or they coincide. But they have coincided because they are equal. So therefore, the quotient partitions S. And therefore, we have completed the proof of the theorem. Okay? So that completes the proof of the fundamental theorem of equivalence relation. Again, you will need to be able to state it and also prove it as you have on the screen. Okay, let's move forward now. I have an example here. This example will show practically the use of the posets, the definition of a poset. You remember what a partial order was. A partial order is one that has the relation that is what? Reflexive, transitive, and antisymmetric. Okay, so we want to check that quickly. Okay, so we are given a set S which contains this element, and the relation is defined on it in such a way that it combines elements only strictly by this 1 1 1 2 1 3 1 4 2 2 2 3 2 4 3 3 3 4 and 4 4. Those are the only elements in this relationship, that's its preceding relation. Okay, so we want to determine if this our set is a poset. So we want to check if it has a partial order. So to check for a partial order means that we'll have to check if it satisfies, if it is reflexive, transitive, and antisymmetric, right? So now we know what reflexive means. It means that A will have to precede A. As for reflexive, for it to be transitive, it means that A will precede B, B precede C, meaning that A would then precede C, which implies that will hold. And the final one, which is antisymmetric, means that you have that A precedes B, B does not precede C, means that A must be equal to B. B does not precede A, means that A is equal to B. Okay, so let's look at the screen. We go over it, which is what I've written here one by one. So we have to check each one of them, all of this one by one. So our elements are, for our poset, this is the condition for it. It can only satisfy all of us, right? So we want to check if it is reflexive. For reflexive, we seek that A is XX, all of its elements must be in our set, okay, under the partial order. So let's see, when we have XX and X is equal to 1, what do we get? 1 1. Is 1 1 in our set? We get 1 1. Is 1 1 there? Let me clean this so that we check carefully. Clearly 1 1 is there. Look at 1 1 right here. So it is contained in it. That's why there's a containment element in it right there. Next is when X is equal to 2. When X is equal to 2, is here 2 2? Yes, see 2 2 here. So 2 2 is in it. So that's it. That. What of when X is 3? Because the highest number is 4. You can see that. So when X is equal to 3, there's 3 3. Yes, this is 3 3. So contained in it. And finally, X equal to 4, which is 4 4. And 4 4, where is it? Right here. So complete. So all elements X equal to 1, 2, 3, and 4 are all contained in our relation. Therefore, it is reflexive. So we're proving reflexive. Now we need to check the second one. So I've brought it out in icon here, so we're through it. Reflexive. We want to check if it is transitive. So is it transitive? Let's check. So for transitivity, we need to check that if A precedes B and B precedes C, therefore A will precede C. Let's check. So we check for each of the elements one by one, or just even pick just one of them. Once we have one satisfied, we're good. So let's check. So we need to check it is transitive. That is this. Okay. Now we seek X, Y, Z, and if X, Y is this, then all of that. So here we have chosen 2, 3. Okay, I'm sorry, 2, 3. So for 2, 3, we also picked 3, 4. You can choose any one of your choice and see. So there's 2, 3. So 2, 3, and then there is a 2, 4. Where's 2, 4? Yeah, it's 2, 4. So it means that I have a relation from 3, 4. Better, because 2, 3, the next one would definitely be, we want A B, C, right? So that's 2, 3, 4. Those are the elements we're looking for. So 2, 3, 4, and the combination is there. So we want to see if there will be 2, 4, 2, 4. So is there 2, 4? Let's check. There 2, 4. Yes, this is 2, 4 right here. So since there's 2, 4, 2, 4 is right here. So since there's 2, 4, it means that it satisfies transitivity. The transitivity is nicely sorted. The next and final thing we need to check for it to be a poset is that it is what? Anti-symmetric. So is it anti-symmetric? Let's check that. So finally we check 3. That is A related to B, B not related to A, then A equals to B. So let's check that. So we pick 2 elements. You can pick any one of your choice anyway. So we pick 1, 2. So 1, 2, is there 2, 1? Check. There's no 2, 1. There's 2, 2. There's 2, 3. But there's no 2, 1. Clearly 2, 1 is not it. Therefore it is anti-symmetric. Hence it is a poset. And that completes the solution for this example. Okay, so again, you can go through the examples again and ask questions on the WhatsApp group if you have issues with understanding the examples and the theorem proven earlier on. Okay, next we go into what we call the inclusion diagram. The inclusion diagram is basically like diagram that shows the greatest element, least element, maximum element, and all of that. But let's see how to see that, visualize it using an image. Okay, so the question says, draw the inclusion diagram for the divisors of 12. Which of the elements are maximal, minimal, greatest, and least? Okay, so we want to find out those. So to draw the inclusion diagram, we want to find all the elements. So you could use your factorization method to find all the possible elements of 12. And the possible elements are 1, 2, 3, 4, 6, 12. You can verify that yourself. Now we'll now check each of the elements one by one so that we can get the inclusion, how each one goes into each one of them. We start with the greatest of them and the largest of the elements, and the largest is 12, right? So 12, what are the factors of 12? Clearly 1, 2, 3, 4, and 12. And 12 is not contained in any other larger element. It's just itself, so it's not contained. It's the biggest of them all. Okay. Next to it is 6. So what are the possible factors of 6? Clearly 1, 2, 3, and 6 itself, right? And these are factors of 12, right? So it means that 6 will be contained. It will be a subset of 12, right? So it is below 12, just to help us figure and arrange it. Next is after 6 is 4. The next element is 4, because we've done 12, which is the largest. So we go next to 4. For 4, what are the factors of 4? Clearly 1, 2, and 4. And these are factors of 12, right? Because 2 would divide 12, 4 would divide 12, and 1 also. So they are factors of 12, meaning that 4 is a subset of 12. It's not a subset of 6 because 4 does not divide 6. Not even its factors can. Okay, so it's a subset of 12. Okay, because of that. The next factor is 3. 3 has factors 1 and 3, right? And what are they factors of 12 directly? Let's see what they are. If you check, it's not a factor of 4 because 3 will not divide 4. But it is a factor of 6. And it is a factor of 12, agreed? Because it divide. 3 will divide 6, 3 will divide 12. So 3 is a subset of both 6 and 12. That's what it means there. Okay, sorry, my image has covered the 12. So it's a factor of both 6 and 12. So it's a subset. It will be right under 6 and 12. Okay. And the next factor is 2. We're almost through with checking each of the factors. Now 2 has factors 1 and 2 because 2 divides 2. And these are factors of 4, 6, and 12 because 2 divides 4, 2 divides 6, and 2 divides 12. Meaning that 2 is a subset of both 4, 6, and 12. So it lies under 6, 4, and 12. Maybe not subset. Maybe I would have used the word that it lies under. Okay. And the final factor, which is 1. 1 is just 1 as a factor of itself, but it's a subset of every element, as in 2, 3, 4, 6, 12. Okay. So it lies under 2, 4, 6, and 12. And again, element 12 has no subset. It's the largest of them all. So let's see it in pictorial form right here. Okay, so based on what I had said earlier, based on all the solutions, I'm trying to clean so we can see everything well. From this final conclusion, you see that 6 is under 12. So that's why it's here. And the arrow is pointing that it's under 12 here. Next is 4. 4 is also under 12, but not under 6, right? So I don't want it to be under 6. I want it to be directly under 12. That's why it's on this side with the arrow pointing to 12. Okay. So we are through with 4 and 6. They're just up there. Next is 3. 3 is under both 6 and 12. So 3 is under both 6 and 12. So you want to put it here because it will go into 6 and 6 it will go under 12. You see that? And next is 2. 2 is a subset of 4, 6, and 12. So it cannot go under 3. It has to go in such a way that it links up with the others that are there. So that's why there's an arrow. There's 2. It is under 6. It's under 4. Okay, so you can see there. Okay, that's how to arrange it nicely. I'm sorry, let me clean it. Okay, so we finished 2 and 3, and the final one, which is 1. We said 1 was inside all. It lies under all, so that's why 1 is down here. It's under 3. It's under 2. And it's directly under 12. And because it's under 3, 3 goes into 6, 6 goes into 12. It's under 2, 2 goes into 4, and under 12. So that's how we got the diagram. Okay. And in fact, remember 2 goes into 6, so 1 still goes all the way. Okay. So that's how we got our diagram. So now we can answer the next question. So we finished drawing our diagram. The question says, which element is maximal? Clearly, using the inclusion diagram, we see that the maximum, the biggest of them is 12. So that's how we got 12. And the minimal is 1. It's right down there. Okay. The greatest element is 12. It's the biggest too. It's just lying up there. Just looking at it up there, it's there. And definitely the least element will also be 1. Okay. So that's the answer to that question. Okay. Let's go to the next example. But the next example is also an inclusion diagram. But now we have some rules again. So which of the elements of the post set? So we have the post set. It has elements 2, 4, 5, 10, 12, 20, 25. Okay, so which of the elements of this post set are maximal elements, minimal elements, greatest element, and least elements? So we need to find all those elements. So just like we did in the previous example, we have to check each of these elements. Now we are given the factors. We don't need to factorize, so we are given the factors. So, but then we'll have to check how they are contained. So we start with 25. So 25, what are the factors of 25 in this list? Okay, so we check. 25 has factors. It doesn't have 2. What did I do here? It doesn't have these factors. Not true at all. This is wrong. 25 has no factor. It has all these other factors, right? It has 5. Let me just clean it. I made a mistake here in my typing, so everybody note that 2 is not a factor of 25. Clearly, it's an odd number. Neither is 4. Okay. Neither is 10. Neither is 12. Neither is 20. Okay, but we have 5 and 25. Everyone take note of my mistake. It's a mistake, it's a typo. But you know what, 25 has no others. It's not a subset of any other element, right? It's just there alone. It doesn't have others. Okay, so let's go to 20. I haven't finished with 25. The next biggest factor in our post set is 20. So for 20, it has factors. What are the factors? 2, 4, 5, 10, and 20. So you stick to this list to get your factors. Okay, they are all factors of 20. But what of 20? Is it a subset of any other element? No, it does. It cannot lie under any. It can't lie in 20 because it cannot divide 20. Okay. After 20, we go back to our list again. We're through with 20. We go to the next, which is what? 12. 12 has factors 2, 4, and 12. They're all here. 2, 4, and 12. So you checked. You make sure you're following the post set you're given. Okay, you check it. So 12 has factors 2, 4, and 12. And guess what? 12 can you divide anything? 12 cannot divide the bigger ones. It cannot divide 20. It cannot divide 12. So 12 stands on its own. So we have 12 standing on its own, 20 standing on its own, 25 standing on its own. Next element is 10. Okay, let's look at 10. So 10 has factors 2, 5, and 10. Is it true? Look at it from the set. Over here we have 2 can divide 10, 5 can divide 10, and 10 can. So that's how we got the elements there. So 10 has factors 2, 5, and 10. And these are factors of 10 and 20, right? Because 2 and 5 and 10 can divide 10 itself. It can divide 20. So therefore 10 can divide 20. So it is a subset of 20 to lie right under 20. Okay. Next factor we're through with 10 is 5. Let's look at 5. What are factors of 5? 5 is a factor of 10, 20, and 5 and 25, right? So it lies under them. So 5 is a subset of 10, 20, and 25. What of 4? 4 has factors. So it's factors of 5 are just 1 and 5, not 10, 20. It has 1, 5. Okay, well, factor 5 is still correct. Factors 5. Okay. Oh, sorry, let me clean it, not make it dirty. Okay, come backwards. Okay, so let's continue. Let's I need to clean this, it's not going off. Okay, let's just continue if it wouldn't go off. What have I done? Sorry, I'll get us back on the page we belong to. Okay, there we are. Okay, so let's continue. So for 4, factors of 4 are 2 and 4, and 2 and 4 divide which other elements? They can divide 12, they can divide 20. So that's why 2 and 4 are factors of 12 and 20. So meaning that 4 lies under 12 and 20, right? And finally, the last element, which is 2. You can see 2 has a factor 2 itself, and it divides 2, 4, 10, 12, and 20 in our list of our set up there. Therefore, 2 lies under 2, 4, 10, 12, and 20. Okay, so we are through with all the factors, all of them. We've sorted them here. So we now draw our diagram. So how would the diagram look like? We know that 25 stands alone, 20 stands alone, and 12 stands alone. That's why you see 12, 20, 25 up here in the diagram. We know under, so they're standing alone. We know that under 10, under 20 is 10. So 10 is right here. Can you see with the arrow pointing that I'm under 20? Next is 5. 5 is under 10, 20, and 25. So 5 is right here. Can you see? It's under 25. And it goes into 10, 20. So that settles that 5, right? So we're through with 5. Next is 4. 4 is under 12 and 20. So we put 4 right here. Is under 12 and is under 20. That's why the arrow is pointing that way. And finally 2. 2 is under 2. It's under 4. So that's why it's right here under 4. Let me clean the screen. Two is under 4. It's under 10. And it's under 12. That's why it's going all the way up. And it's under 20. So you can see it just joins up there. Okay. So that's how we got that. And we're through with the diagram because there's no other element. Okay. Those are all the elements. And that's our diagram. But then we're through with the diagram. We need to find what is the minimum, what's the greatest, right? Okay. So what is the minimum? The minimal elements are, from the diagram we see that the maximal element, this is the biggest of them all, right? Which is 12, 20, 25. That's how we got that. What are the minimal elements? They're the ones at the lowest, which is 2 and 5. Clearly, there's no element that is bigger than 12, 20, 25. They're all at the same power. Neither is there any smallest one, 2, and 5. So there is no greatest element and there is no least element. And that's how we got our solution. The diagram, the solution. Again, you can go through, pause, rewind, play the video over again, ask questions if you have questions, and that is all to inclusion diagram. Okay, let's continue. Next is what we call lemma A. And for lemma A, I think it's 2 point something in your lecture notes directly. But this lemma states that if we have a function a that maps a to b, and another function g that maps b to a, and they are mappings that satisfy the composition that f of g will give us the identity on a, then f is injective and g is surjective. The proof is very easy and straightforward. First, we have to prove that f is injective. Now, if you remember in Math 101, if you want to prove something is injective, you take f of x equals to f of y, means that you will seek, your target is to show that you will get that x equal to y. So that's our target. So our notation is we took the function the opposite direction, which is x y equals to y. So just basically f of y and f of x. Our target is to show that x equal to y. Okay, so let's see how we're going to do that. Let's clean this. Now we know that our mapping satisfies the condition that f of g is equal to 1. Okay, so clearly x is same as x times 1, right? But what is 1? 1 is this here. So that is x into f g, right? Okay, so by the time we do our composition, mapping, this associativity of maps, we get that x, f, and then we get g, right? You've seen that? So if you have x, f, g, we know what is xf from this. We had said that we suppose this to be equal to this, right? So wherever xf is, we are putting yf. So this will now be yf and then g, right? So if we equate it and do our composition, you just get f, yf, g, right? So you can bring this together and your final answer will just be y times 1, which is same as y. Okay, so let me read what I've done. So some steps are missing as you have seen me write, but you'll get it as you look through, and I'll take it again. So x again is equal to x times 1, right? Which is same as x, and 1 is fg from here. So we continue here. So composition allows me to do this composition mapping, but I know what xf is. It is yf. So that's how we got yf here. And composition allows me to mix it again, but you know what fg is. It is 1 here. So wherever there is fg, it's 1. So therefore we get that x equals to y. So whenever xf is equals to yf, x is equals to y. And hence f is injective. So we've shown it is injective. For surjectivity, that's quite as easy as what we've done here too. Basically, we want to show there's an image somewhere for surjectivity, right? So we have that. We know x is the same thing as x times 1, right? Oh, well, this is the same as x, fg, right? Well, then this is just simply x, f, is that? And g. Clearly it is surjective, and that is all to the proof. As simple as that. Okay, so that's how to show prove lemma A. I would need you to be able to prove lemma A because it is called in the next theorem. This theorem says that a mapping f that maps A to B is a bijection. Now you know what a bijection is, because I remember saying you should check the lecture notes or your Math 103. A bijection mapping is one that is both injective and surjective. Okay, so it's saying it is a bijection if and only if the mapping G that maps B to A satisfies the condition that f of G is equal to the identity on A and G of A is equal to the identity of B. That's the first part. So it's an if and only if condition, and which means we have a biconditional statement there, two-way proof before us, and it has another part to it. So there's the A part, which is it stops here, and there's another part to it, the second part, which says moreover there can be only one mapping G to satisfy the condition FG that satisfies this condition. So only one. So once you are told only one, you say there are two. whenever you're proving. You assume there are two and then get a contradiction. Okay, so we have two parts to prove. First, we have to prove the part that says we have a bijection if and only if the condition this is satisfied, and the other part says that there's just one condition for one G that will satisfy the mapping. Okay, so we have to prove the first part and then the second part. So let's prove the first part. For the first part, because we have an if and only if, it means we have this arrow. Okay, so we have to prove either this way first or this way first. So let's see what I started with so that we can stick to the notes. Whichever one you decide to prove first is okay by me. So since the statement of the theorem is biconditional, we will have to prove in two directions. So first, we will assume that the composition mappings hold. That is, we're going to say that this condition holds, so that we can show that it's a bijection, right? But then if we have this condition holding, guess what? We have proven it from lemma A here. Once we have a mapping that is injective and surjective, we say it's a bijection, right? And it satisfies this condition. In fact, it satisfies for this G F to be equals to 1B, right? So we can conclude that one right away, straight. So first we suppose this holds, and then F is both injective and surjective. So by lemma A, and that's by lemma A. Hence, it is a bijection. So that's how I got the proof of the first part of the arrow. So we have assumed that it has a composition, and then by lemma A, we're able to show that it's a bijection. So next, we need to accept that it's a bijection, and then prove that we'll get the mapping this. How? So let's see how to go about it. So conversely now, that is proving the opposite direction. We suppose that F mapping A to B is a bijection. We want to prove that F of G will give us the identity on A, and G of F will give us the identity on B. So since F is a bijection, it means I can find an element U in B, okay? And we can find X such that this mapping will be equal to some to U. So that is, I can find X such that it will map to U because it's a bijection. You know, it is injective, it is surjective, right? So if that is the case, I can do this manipulation. I just take the function F inverse. It's a bijection, so I can do that. Like if I multiply by F inverse equals to, so F inverse on both sides. F inverse on both sides. I'll get what I have here. Okay, you can pause the video and attempt that yourself. Okay, so you get the F inverse, so you get this to be that. And because it's a bijection, I can have UG to be equal to X. And then you repeat the same procedure by, so UG equal to X. I can take G inverse on both sides, of both sides. So now be, so this is X, right? This will now be X, G inverse. Okay, so this goes to identity, so that's how I got this one here. Okay, so our target again is to show that you will get the identity maps for both cases, right? Because we already said it's a bijection. So using these two results I obtained from the fact that my F is a bijection, these two we're going to continue to prove. Okay, so now using this now, UG is equal to X is the same thing as UG equals to UF inverse. How did I get that? Because I know that X is this, right? That's what this is. So okay, so if I multiply both sides by F, this side multiply F here, multiply F here, you get this next line here. This goes to identity, right? That's how I got this term here. Can you see that? If I happen to have UGF equals to U, it means that this is U times 1, right? For it to be equal to U, meaning that G of F is equal to 1. So we've proven the first identity here. We've proven this. So that satisfies the first one. So we need to prove the second one. So let's go to the next slide. For the next slide, we have that X of F equals to U. You know I got that from the beginning there. And we already know that U was X G inverse. Let's check that out. So where did I write that? Okay, this is it here. Sorry, let's clean the screen a little so you can see it right here. Okay, so it's all coming from this identities here that we had gotten from the fact that we had a bijection, right? Okay, so X when the mapping F carries F, it takes it to U because of the fact that we had a bijection, and we know that U is the same as XG inverse. So whatever I do, I take this is U, F equals to UG. So I'm supposed to have written this for you. F U X, this is equals to U. I didn't write it, so let's do it quickly here. So I have X F equal to, wherever I see U, I put XG inverse, right? So XG inverse. So how did I get this next line here? I simply multiplied by both, took the function composition, composed both sides by G. Okay, so this is G inverse, right? And this is G. Okay, so that's how I got this line here. So let's continue from there. So this goes to identity, as in this one goes to identity. That's how we're left with X and this composition. So this is just X F G equal to X. Again, you can see for this X to be on both sides means that this thing is equal to 1. So that's what I've written. So FG equals to 1A. Okay. So we've proven the two identities. That's what it means. We've proven the two compositions and gotten the identity map, proving that they are both equals to the identity. So finally, okay, sorry. So we have this satisfied. Okay. Now I told us earlier on that there's a second part to the theorem, right? The moreover part. This moreover part says that there can only be one mapping G that will satisfy this condition. And I said once you're told there's one mapping, do what? Assume there are two mappings, right? Okay, so we assume there are two of them. So that's what we're going to do now. So finally, suppose that this condition is satisfied by G and that there's another mapping G prime that takes B to A. And it's another mapping. So that, look now, FG prime, can you see that this was FG, but now this FG prime is equals to 1A, and this was GF. Now this is G prime F equals to 1B. Don't mind the sign of the binary operation missing. It means the same thing. Sorry, I made that mistake. So you don't get confused. They're just about the same definition. That's what it means for mine. Okay. Okay. So we want to show that we'll get the same answer. So by associativity, I have that G prime is same as G prime times 1. Do you agree that? Remember that I said G1 is the same thing as saying G prime, well, it's the same thing as G prime times 1, because 1 times anything is going to give me back 1, right? But we know what 1A is. What is 1A? So we choose any of the 1A's with the target of showing that G prime will be equals to G. Okay, so we pick the 1A. I won't pick this one. Why? Because there's G prime here. I want to pick the one that doesn't have a G prime, which is this one. So that's why there's FG in here. So wherever you see 1G, replace it with FG. Why? Because FG is plus 1A. Do you understand that? Okay, so with that, we then do associativity, and then this becomes, so let me do this for you. So we have G prime, FG. Associativity allows me to do G prime, F, G, right? But you know what G prime F is. Where's G prime F, CK? G prime F is 1. So this is going to be 1 times G. Okay, but then we started with G prime equal to this, right? So that's how I got this here. And finally you get that G, because 1G is same thing as G, which is same as G, right? So G prime is same as G, as you can see there. Okay. So G prime is same as G, means thus there can only be one mapping G. Can only be one of them. Because when I said there were two different two of them, I said that satisfy the same map. We got that G prime would be same as 1 and G prime times 1. We know the 1A, we choose the one without the G prime, which is this, inserted it, and the associativity allowed me to do this. But I know what G prime F is. It is this one here. It is 1B. So I put in the 1B, which is the identity, and 1B times A, 1B times G is just G, meaning that these two are equal. And if the two are equal, it means that there can only be a G that will satisfy the condition, and we're through with the proof of the theorem. So again, note this, in the proof of this particular theorem, we needed the knowledge of lemma A. During your exams, if you tell me by lemma A, I will ask you what is lemma A. So you should be able to state lemma A and also be able to prove it. Okay. I think that's that for our video for today. Thank you.